Hello, everyone. I'm back. Um, this is section 3.2. 3.2 is titled Differentiability. It's a really quick section. It's going to be really quick. Normally, I would spend a little more time in this section with the math behind it, but I think in order to save some time this year, we're going to skip that part of it. It's not as super important. The basic idea of today's lesson is just when does something have a derivative, period. It's called differentiability. So if a function has a derivative, it is differentiable or has differentiability. If it doesn't, then it's not differentiable at that point. So we're going to talk about when that might occur. So you're going to get a lot of questions, and a lot of our theorems actually say is something has to be continuous and differentiable for our theorems to work. So what does that actually mean? It just means has a derivative. Okay. So what we're going to explore today is when a function might not have a derivative. Okay. You probably learned some ways to take derivatives last year. You might remember that the derivative of x squared perhaps is 2x. What does that exactly mean? We'll kind of talk about that a little bit more as we go on for sure. You can get that using the definition of derivative, which you may or may not have been able to do in some homework problems. But we're going to look more at pictures and graphs. What does it mean for it to not have a derivative? And what we're going to do is we're going to backtrack to slope. So if we just remember derivative means slope of tangent, if a function's picture doesn't have a slope of a tangent at a point, then it doesn't have a derivative. So when does that occur? So there's basically 4 times when this occurs. Generally speaking, the first one is what's called a corner. So any graph that has a corner like that, I think I drew this picture basically yesterday, or it's the same idea with the slope of 2 and the slope of -1, that if you look right at that corner right there and you try to draw a tangent line, there is no one tangent line you can draw, right? You can draw it horizontal, you can draw it this way, you can draw it that way. I did this yesterday, so I want to do it again. So there is no derivative there, because remember, if there is a derivative, you got to be able to tell me what the slope is of that tangent, right? So everywhere else, along here, totally good, has a slope, but not at the corner. Where do you get corners? The most common place for corners are in absolute values. You probably remember y equals the absolute value of x, looks like a v. Any absolute values typically have these in them. You can force corners with piecewise functions. In essence, that's a corner also. Okay, that usually just comes from a piecewise function. Erase that because I need some space for the next one. The next one, and the corner could be anywhere too, right? The next one looks like this. This is actually called a cusp. Okay, it does not have a derivative at that corner, again, at that cusp, for the same exact reason the corner doesn't, right? There is no slope there. Notice as I draw on, it has slopes, 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 it has slopes. But when you get to that one spot in the corner, you can't draw one tangent line. So that's called a cusp. Go back to the purple for you there. The next one looks like this. This is called a vertical tangent. If you think about that point right there in the middle, and you draw a tangent line, so notice tangent line here, tangent line here, tangent line here, those are all tangent lines. When you get right here, that tangent line is going to be vertical. And if I were to say, what's the slope of that? It would be infinity, right? Which is in essence like dividing by 0, hence no derivative. So if there's a vertical tangent, there's no derivative, okay? And then the fourth one, I'll go back to is just what we call a jump issue. So anytime you have a graph that jumps, there is no derivative at that point. And I hope that's obvious, because where do I draw the tangent line? Do I draw it on the one with the open circle? Do I draw it with the one in the closed circle? And if they both happen to be open, which it could be, and a point down here, then where do I draw it? These only really occur in piecewise functions, which we don't deal with very much. We deal with them a little bit. So these are the 4 cases graphically when something doesn't have a derivative. Real quick, I just want to show you the math behind it. It's not something you're going to have to do, but I know some of you like math, which is good. But each one has a little math idea behind it. So what I mean by that is algebraically, what's causing the cusp? So I'm going to go through this really quickly. If you want to slow it down or look at it afterwards, that's fine. In the corner, if you notice, the two tangents have different limits from each side, right? So if you have a corner, um, you have a corner, tangents on this side are positive, tangents on this side are negative, or vice versa. Okay, even if it's a corner that, let me draw another one in here for you that looks like that. Tangents from the left are different from the tangents from the right. That's all that says. Limit as x approaches a from the left of the derivative. Notice of the derivative, which is the slope. So the slopes are different from the left and the right. That's the math behind it. And remember that derivatives are slopes, so the slopes would have to be the same. The cusp, the limits are different. The limits are different from both sides, and one's always infinity and one's always negative infinity. So on the corner, the slopes could be anything, 1 or 2 or -1 or -3, but on the cusp, if you notice back here with my green lines here on the cusp, or orange line, sorry, positive slopes on that side, negative slopes on this side. As you get closer and closer to the cusp, they both get closer and closer to either infinity or negative infinity, whichever one you have. I just said, or vice versa. One of them has to be infinity, one of them has to be negative infinity. I'm going to jump to vertical tangent because vertical tangent is similar. Both of the slopes, this case, are either both positive or both negative. So if you look back at the picture I drew up here, notice positive slope, positive slope, positive slope, positive slope. They're all positive slopes. If I tilted the picture the other way, they'd all be negative slopes. But the idea is in the vertical tangent, they're just infinities from both sides. And then the last one is the jump. There just is no limit of the function. There's nothing going on there. That should be clear. Again, all of this idea of the math behind it, not super important. It's interesting for sure, and I would probably go a little bit more in depth at normal years if I was in a classroom, but there are some things we're going to pick and choose this year. You would never see the actual math on the AP test anyway, the algebra, but you do need to know what's a corner, what's a cusp, what's a vertical tangent. If you see it in the picture, cusps are often caused by square roots. Vertical tangents like cubics. But more important than anything is you just need to be able to look at a picture and tell when it's a corner, when it's a cusp, if it has a tangent line or if it doesn't. It's all called differentiability when something has a derivative. So that's it for section 3.2. Let me know if you need any help.